Hey, John here, making some progress today on a PS2 interface for the Project Nouveau board. So here's my setup right now. I've got this pair of transistors down there, a pair of 2700s. Those are 2N2700. And I've got some pull-up resistors you see there, winding around with this cable through here, looping into the top of them there. Got my scope probes in there, and I'm taking power off of the FPGA board, which come from the Pi, and I've got it connected up to a PS2 connector right there, and a nice anvil holding the cord, because every time I touch this cable in any way, it moves and everything pops off. So always good to have an anvil around, a little teeny one in this particular case, to hold things tight. Now that cable runs over to here, an ancient keyboard that I dug around and found in some boxes downstairs. This I used to have hooked up to a KVM back in the old days because it's nice and narrow and fits on a shelf in a regular rack, unlike normal keyboards that are always too wide and enormously difficult to use in that scenario. Today, I guess you'd use one of those drawer keyboards and whatnot. But this was, in the 90s, that's what we had.
As always, a huge thanks to all the supporters of my channel, especially the VIP patrons listed here. Now let's look a little more closely at a schematic version of what you just saw on that breadboard. Here I've got my connector here that plugs in a PS2 keyboard. Usually this would be your purple jack on the back of your PC or something like that. Now I'm going to lay out an interface for a board, and I'm thinking I'm going to go ahead and put down some 0603 capacitors, which I probably won't ever populate, but it'll be nice to have them there just in case the signal comes in off this jack and it overshoots or rings or something like that. I can use that to dampen it down a little bit, take the offshoot out, slow down that slew rate if it turns out to be necessary. Now, a keyboard is an open collector driver with a pull-up resistor in the keyboard. I'll put a link to this description on how level shifters work, which is hosted at DigiKey. They give you these drawings and they talk about it. They tell you why it works, how it works, and all this other stuff. I used one of these in another project I did for the Z80 Retro when I made a Flash programmer. I did the same thing. They got a kind of a neat option here in the end down here where you double up the FETs. They talk about this if you're going to risk having one of the endpoints powered down. I used a different technique on my design, but this is actually a pretty good idea. Really simple. Anyway, I'll leave that to the viewer. If you want to look closely at that, you'll have a link to it. In any event, I use the same design here. You got to pull up in the keyboard. You got to pull up on the local side here as well. This is your 3.3 volt signal, and you've got your 5 volt signal over here. It's bidirectional because sometimes the host will generate a clock and send it to the keyboard. Other times the keyboard generates a clock, sends it back to the host. And the same thing happens with the data. It's a bidirectional type of thing. A lot like what happens with I2C, which is what I used on the Z80 Retro project the last time I talked about this on my channel. These resistors are also likely to be unnecessary because the FPGA has pull-up resistors that I can enable if I want to. But there may be some issues with that. When we get to the code, we'll look more closely at what's going on there. I think I mentioned it before. The open source tools that I use don't always infer the bidirectional driver right in the cases when you have a pull-up resistor involved. You have to be careful because Yosis they don't have a sophisticated set of software to support that yet. It definitely works. You just have to be careful. You got to be knowledgeable that the pull-up resistor doesn't work unless you kind of manually configure it in your code. Regardless, the pull-up resistor inside the FPGA might be too high a resistance value to work cleanly or properly. So again, I'm going to throw down extra footprints over here on my final design, not the final design, but my first draft for my board, the I/O interface board that I'm going to use with my my FPGA board. So I can put smaller size resistors in here if necessary. My gut tells me I won't need either these resistors or these capacitors, but the last thing I need to do is have a mess on my hands. I'm going to go ahead and put footprints for them anyway in there, okay? So this is the schematic drawing of the pile of cables and jumpers on the breadboard that you just saw. Everything's on there except these capacitors are not. I think I have 5.1K ohm resistors. These are nominal. Anything over 1K and less than about 10K should be fine in here if you don't have these exact sizes. I do not have this in the circuit on my breadboard. This is going to be one of those PTC fuses. Ultimately, I expect a 50 milliamp. I don't know how much I really would need. We'll look at the PS2 interface spec in more detail later on, because you don't want to have a situation where this might short out your, in this case, my 5-volt supply. This is going to be the main power supply coming into our board ultimately off of a USB jack, which will use the power of this thing. And if there's a problem, it'd be nice to not have it kill everything. So I'm going to go ahead and throw a footprint down for this a PTC fuse in there as well. Again, if you don't want to put a fuse in there, you can always just put a little piece of wire over it and not bother. Again, footprint it in case I want it kind of a situation. Let's look at another interface for a PS2 keyboard before we get too far along. As you might have done one of these yourself, and you might say, who cares? You don't need all that stuff. You can just put some series resistors on here like that to limit the current and make this thing 5-volt compatible, and even, with an FPGA. Now, this is right out of the Spartan 3E starter kit circuit, this evaluation board. I have one of these. This was my first FPGA code, my first Verilog experience was with this board. And this is all they do. Now, why didn't I do this? Well, the answer is that the Spartan 3E FPGA has different input clamping diodes than the ICE 40 series chip from Lattice. Now, there's some talk on the internet about how Lattice purchased Silicon Blue. I mentioned that some time ago, that, all their the older dock all said Silicon Blue in it, and then they changed it over and now it says Lattice. They obviously bought Silicon Blue. I think that Silicon Blue, based on the chatter that I saw, had in their portfolio products all the ICE 40 chips, which makes sense because all the silicon technology inside the ICE 40 had all the Silicon Blue dock associated with it. My point is that there's some talk about how when Silicon Blue provided these products, they advertised them as being 5-volt tolerant. And because they were based on those earlier designs, even if they're not 5-volt tolerant anymore, some people did some tests and experiments to notice that they don't have clamping diodes in the way they normally would if they were not 5-volt tolerant. So they might kind of still be, but they're not documented as such, and so it might act in a weird way. So my point is, we want to use level shifters, actual level shifters. You could do this if you knew that the circuitry over here on the right had clamping diodes on it. Now, I could also just put a clamping diode on there myself. We could, if we wanted to, forego the MOSFET here, put a clamping diode between this line and the 3.3 volts and a series resistor on it. Well, the series resistor would actually go over here. The clamping diode would go on the FPGA side of things, okay? So that would be that this line would never go above 3.3. You'd have a series resistor over here. So when the 5 volts came in here, it would be current limited by your series resistor. In the case of the Spartan 3E, they have a 270 ohm resistor in there. And then a diode up to the 3.3 so that it would clamp it at 3.3. So if this thing ever pushed it down to ground, it would look like ground over here, because there's nothing really pulling it up to 3.3. and it would flow right into the FPGA. Now, the FPGA might have a pull-up in it and stuff like that, and you got these dividing resistors, and I don't know. Maybe it's a good idea, maybe it's a bad idea. The Xilinx engineers, or the Digilent engineers that designed this particular board, felt that this was a perfectly fine way to do this. They have tons of code that they wrote, and it works fine, so that might be fine, but only if you have clamping diodes on your board. I decided to go with a full level shifter circuit because it's really about the same price anyway, and it's certain to work and cure whatever ails you. All right, so this is the way I'm going to do it. Now, let's scroll down a little bit. They talk about how they pin out the connector, what they connect up the pins. I do this is the same way I did it, same way everyone else does it, okay? Then down here they talk about how the signals look that are coming and going on the clock edge should fall during the stable time of the data signal. You know, after the setup and hold time here. We should have a valid sampling time if we do it on the falling edge of the clock, okay? Now, it ticks a bunch of times, and there's a parity bit at the end. I think it's odd parity, and there's one extra falling edge. There's a stop bit. So this looks a whole lot like a UART type of signal, but it comes with its own clock. So it doesn't have a standard bit rate or anything like that. It's synchronized to its own clock. And they observe that the time of the clock is anywhere between 30 to 50 milliseconds. That's a pretty wide range. The setup and hold time is anywhere between 5 to 25 microseconds. Now, these are a long time. So we need to use this clock. We cannot free run and expect to recognize this. Any keyboard might have different timing, okay? So this is synchronous serial data. They provide their own clock. This doc continues on. I'll put a link to this thing in the description below on this video if you want to see it. This is described all over the place. PS2 interfaces to FPGAs are one of these. It's like VGA. It's a common thing. It's a rite of passage. A lot of students write these in college courses. It talks about how the keyboard works. A nice brief little summary here. It says, when you press the key down, you get a character, or 2, or 4, depending on the kind of key you press in your keyboard. And then you get another character when you release the key, or 2 or more. All right? So that's described in here. You press the key, you see something, you release it. What you get is you get an up key code, which is an F0. And then, after that, it sends you the same character code of the key that you saw earlier when the key went down. So you get a single word, single byte value. When you press a key, when you release it, you get a double. You get an F0 followed by the key when you release it. It also talks about the fact that the shift key is just another key. The shift key does not change the codes that the keyboard sends. The shift key itself is just a key, and it'll give you a down and an up code. So you got to keep track that you saw the shift key go down and interpret the key codes yourself that come after that and before you see later on the up code for the shift key being released. Same thing with the control key. Any of the keys on the keyboard do this sort of thing. So here's the thing I alluded to, and I said, or more keys and stuff like that. They have these extended keys, because, 256 is not enough, I guess. So they have the extended keys. They can send an E0 and then a scan code. And notice here it says it could send more than one scan code. For example, one obvious key that I've seen is your print screen key. That sends like a total of 4 bytes when you press it. And then I don't know what it does when you release it, but it sends a lot more than just the 1 byte is my point. So it's one of these doubly extended things. So when you release such a key, you get an E0, F0, and then you get the scan code again. So you're going to get a 3-byte release, and you might get a 2-byte down, or even more. Now you can look all these up. Even Wikipedia has a page for this. Like I said, this is all over the place. They also give you a nice little diagram on the next page here. If memory serves right. You've got all, like, this is your generic keyboard, right? This is, boy, I don't know what kind of a key this is. This is sort of like the original XT keyboard. They don't have the alpha key, the numeric keypad and stuff over on the right. You don't see the Windows key here and your multimedia keys and all the other stuff that you might see on more modern keyboards. That's probably why you need the extra extended characters and whatnot, okay? So basically, here's your basic. And you can do this by empirically sampling keys on your keyboard, or like I said, I'm sure we can go over to Wikipedia later on when the time comes and just look up all the codes that could ever come from a keyboard. Now, as I said before, the host can also send commands out to the keyboard. And you can ask it things, or you can control things like, the num lock LEDs and all that other junk. So you can tell it to light up the caps lock light, the num lock light, and the scroll lock, and that fun stuff, right? You can also send it a test thingy to have it echo a code back to see if it's working. You can control how fast the keys repeat if you just hold it down. What is this thing? Resend the last scan code. So if you want, you can say send it back, I didn't get it. And you can reset the keyboard. Okay, great. You don't really have to do any of this. If the defaults are fine, and for most retro projects that I would ever want to do, defaults are probably perfectly fine for the keyboard. It comes up, as far as I know, with all this junk turned off anyway, which is usually what I like, as opposed to what a lot of PCs like to do back in the day. Turn on all kinds of crazy modes, num lock and whatnot. I remember the BIOS settings, and it probably still has it today. We can decide when you boot up, do you want these idiot lights on or not? That kind of stuff. That's what they're doing. They're sending out these control codes and setting up the keyboard. So they talk then down here a little more about what it means to use this two-wire interface in a bidirectional fashion. Now, the first time I'm going to use this, I've never actually written code before for this, so I'll figure it out as I go. But I am not really going to control my keyboard. I'm just going to read from it. So in this case, I would be perfectly fine with just a clamping diode and a series resistor, because I don't really want to control it anyhow. But, as we'll see later, we're going to want to do that for a mouse if we want to plug a mouse in, because a mouse, you have to send commands to it. Why it doesn't come online and just give you XY scrolling, I do not know, but you have to dialogue with a mouse in order to get the thing to start talking to you. So let's go ahead and make both of the interfaces the same, is what I'm thinking, because who knows, maybe there's other things we want to do and ultimately control that annoying numlock LED or something like that. So it talks a little bit about that down here. If the host pulls the clock line low, because remember the keyboard has the clock line high as shown up here when it's idle. And it falls down during the start bit, and it toggles while the data is being transmitted, and then it goes high when it's done and stays high when it's idle. Okay? So if you want to send a command to the keyboard that looks like one of these codes, what you do is you simply start running the clock, okay, from the FPGA side. And once the keyboard sees that, it holds off until the line has been idle for a while before it sends its next time, sends the next byte to the host. Same thing will hold true for the mouse. And here it gives you the narrative that it sends an 11-bit word. It is a 0 start bit followed by 8 bits of data, the least significant bit first, an odd parity bit, and a 1 for its stop bit. Clock rate is around 20 to 30 kilohertz, and the data is valid on the falling edge of the clock as shown above. Now, this particular data sheet goes into talking more about how the mouse works, the fact that you got to send it a control signal to get it going, and it talks about the movement in X and Y directions, and the fact that a mouse sends delta values. It can't send absolute because it doesn't really know where it is, but it knows how much it moves when you move it around. So we'll look more closely at this later on when we're working on the Verilog for the mouse. But because the interface for the keyboard and the mouse are exactly the same electrically, it's just the mouse can send different data bytes, giving you, as you can see, like a status. Like this is like the left and right button. I think this is like the direction, the sign bit. Was it going up or down, left and right, and stuff like that, and how far did it move? And all that other fun stuff, right? Plus, if you got a mouse wheel, that's going to do something else. I think that's the Z-axis. I don't know. We'll figure this out as we go. So this will probably be a multi-part series on all this whole thing. Let's just see if we can read the keyboard with a single directional input-only interface that just reads the scan codes. So let's head back to our favorite Verilog examples GitHub repo. I'll put a link in the description below this video on YouTube so you can find your way over here if you want to try it yourself. Now I'm in this directory. Where am I? Top level PS2 right there. This is my PS2 interface. This doesn't currently work. I was going to stub that in. I thought maybe I could shoehorn it into this video. No, that's not going to happen. So don't even bother looking in the reset thing. In the naive interface here, this is the simplest thing I could possibly think of. Dumb it all the way down so we can just see if we can read the codes that come from the keyboard and display them on the LEDs of my 2057 board. So here's my favorite Raspberry Pi, and where I've cloned that repo. If I do a git status on the current directory, I'm up to date. I can go ahead and do a git pull just in case I got no. So I'm good. So this is the naive code here, and I say naive because this does not include a number of things. So don't call me out on the fact that I'm not using synchronizers on the I/O, and the reason is I don't have to because I'm not even going to generate a clock. All right, so let's look at the top level and work our way down. So here we go, top level module. I don't even use the clock 25. S1N I'm going to use as the reset signal here. And remember that on the 2057, when you press the S1N, when the button is pressed down, it's read as a 0, and when you release it, there's a pull-up resistor that reports a 1. And if you look at the PCF file in this directory, you see that on S1, and the little N over there means it's negated. You can't put a bar or an asterisk. There's a lot of conventions people use. I decided to put, in this case, put a underscore N at the end of it. On the PCF file, I said pull up yes, because in this simple situation, we don't have to worry about defining an SBIO module because we're not going to use bidirectional I/O to talk to the keyboard. Remember, so as I said, we're going to read data from the keyboard only. Now, I've had some people look this over, sanity check it, and some have mentioned that there are keyboards out there that won't do what you're going to see mine do today. And namely, if you're following along the retro scene, there's a thing called a Commander X16 that you've probably heard of. And apparently the keyboard that comes with that is PS2, but when it starts up, it's in some weird self-test mode that continuously spews until you reset the keyboard. I'll talk about how you can reset the keyboard when we talk about the mouse, because you got to talk to the mouse. You have to control a mouse if we do a mouse interface down the road, and it'll be the same thing kind of that's going on when you have to reset a keyboard. So if you use the code I'm going to show you here, and your keyboard continuously sends self-test, messages, that I think it's a hexadecimal AA, over and over and over again, just try a different keyboard for now, or wait for the next video when I talk about how we do bidirectional communication so we can reset the keyboard and put it into its normal operating mode. All right? Now, every keyboard I own boots up and goes directly into its normal operating mode. So I didn't have a way to even test the automatic, startup reset stuff that's supposed to reset the other keyboards that like to continuously send self-test data out when they first get powered up. All right, nothing wrong with those keyboards. We just need to do a little more work, which I'm not prepared to talk about today. All right, so just keep all that in mind if yours is doing something weird. Okay, so what we're going to do, we got top level module. I'm not even going to use this clock. I'm not even going to use the second push button. S1, and I'm going to send in my reset signal that goes into my PS2 interface, and we'll look at that in a minute. We have the keyboard clock and the keyboard data signals in here, which you saw in the schematic earlier. So these are declared as inputs. We're going to deal with this one direction only. We're going to read the data that comes in off of these things. The LEDs are going to be used because my PS2, my naive PS2 module, what it will do is it will decode the data given the clock signals as they arrive, and it'll report it back as a 9-bit value on this RX data field here, which I stick into an 8-bit bus, okay, which means the MSB that comes out of RX data will be pruned off, and I'll show you the warning we're going to get from the compiler because these are not the same size, and we'll also look at how to fix it. We'll come back to that. So anyway, the point is I get the 8-bit data value. I'm going to ignore the parity. I don't care whether it's right or not. I'm going to just stick all 8 bits directly into the LED when they arrive. That's all we're going to do, okay? So as I hit the keys, we should be able to see the codes that you saw earlier in the Spartan 3E manual. Note for reference, these are all hex values, obviously, because 3B and 4C and so on. Note that the space is a 2-9. Okay, it's the easiest key to hit on the keyboard, and all the bits are spaced out nicely in binary, so you'll be able to recognize that if I press the space and when we test the code, all right? Okay, so let's look at the PS2 module. Now, I say this is very naive, okay? It's naive because, while this will work, okay, it can get out of sync, and it will never get itself back in sync, number one. Number two, you couldn't really use this in a larger project that has its own, clock and oscillator that's running, because this doesn't have any way to synchronize the data with anything else. Now, you could implement a synchronizer on this output data here before it goes into another part of your circuit, I guess, if you wanted to. But this has enough shortcomings where this is just going to be useful for only testing the electrical interface. That's all we really want to use it for. We'll make a more sophisticated one later on that will time out and reset itself if it gets out of sync with the data coming from the keyboard, because there could always be noise or something like that. This is, like I said, is incredibly naive to think that you would ever want to do this for realsies in a real circuit, okay? But it has an enormous value in its simplicity to just make sure that the level shifter works and that your keyboard's actually talking before I go off and build an actual circuit board and expect to program it and get real I/O going on with it, all right? So what do we got here? We saw these used in the top level module. It expects to get a reset signal. It has the data on the clock. We saw that earlier in the PS2 protocol from the manual we looked at earlier for the 3E. What do we got here? We got the receive data and the receive ready. So the way these are going to work is, as I said a minute ago, when we decode the 8 data bits in the parity that comes from the keyboard, it'll be presented in this output here. And when it has completed, we will assert the ready signal here. Okay? Now this will stay asserted until the clock comes along and starts sending another scan code or something from the keyboard. You'll see the ready go back low again at that time, and then when that code is done, it'll go back high again. And of course, the data will have been updated at that time as well. Okay? Okay, so a couple of registers. This is the receive data register and the receive next. Notice that I've got 10 bits here, and I'm only going to output 8 of them. Well, what's going to happen is when we read the data we get 11 total bits. I'm going to shift them into here, into a 10-bit register, and by doing that, I'm going to throw away the first bit we see, which is going to be the actual start bit. So the rest of them will be, then, is the 8 data bits. It'll be followed by the parity bit, and because of the simplicity of this logic down here, it will also end up having the stop bit in there. So I throw away the most significant bit out of these to give me the 8 data bits in the parity. Okay? What do we got here? We got a 4-bit value to count. This is going to count the number of bits that have arrived so far, so we know when we got all 11 of them, we're done, and we assert ready, and we report the data back to the interface ports, all right? And we have to have a register variable as well to hold this ready flag somewhere. If you really wanted to, you could actually just make this a reg here. I think I talked about that before when talking about Verilog in general. I generally like to make all my ports wires. And if I want to connect a reg up to a wire, I'll do it with the continuous assignment statement elsewhere, which we'll see down below here. So this is where I assign the output values from regs to my ports. And one of the values here is I can then prune that bit off. If you do this when you put a port up here and you want to then kind of play this game where there's an extra bit that you then throw away later on, it'll end up here and it'll mess up your interface. Okay, I'm just saying, just be aware, that's 9 bits. This one's 10 bits, and we're really receiving 11. So there's a lot of stuff going on here, even though it's relatively simple. Okay, what do we got here? We've got an always block. There's going to be a flip-flop that clocks on the falling edge of the PS2 clock line from the connector, okay? And it'll also go if we see a positive edge on a reset. We talked about this before. This is going to be a negative edge triggered flip-flop with an asynchronous reset, okay? So if reset is asserted, even if there's no clock is the point, we'll come through here and we'll reset the register and the count and stuff like that. This has to be asynchronous because there's no other way to reset it unless you hit some keys on your keyboard so that the clock is going while you're pressing the reset button, which is the switch 1 on the 2057 board, okay? So this has got an asynchronous reset to get around that problem. If the clock pulses and we don't have reset asserted, what we're going to do is we're going to move along our usual state machine type of design down here, a regular standard Moore state machine. Down here is a combinational circuit that decides what the next values will be if the clock ticks. So what do we go? You see I got a shift register in here. So what happens is we need to read in 1 bit at a time. Let's go back up here and look at this for a second here. No, they talk about this in brief, okay, because there's going to be your data bits, your parity bit, and all that. And then they got an expanded one when they look at the mouse diagrams down here. So let's ignore the fact that we're really looking at the mouse, but we can still look at these bits. And of course, they don't show you the clock here. Ugh. If we go ahead and Google for this, all right, so you're going to have, all kinds of universities will do this because a lot of them have FPGA courses and or regular old hardware courses. This is from 1999. And quite often in engineering courses, electrical engineering or digital electronics or whatever they want to call it, they will implement interfaces to things like this and VGA monitors and stuff like that. We've talked about that before on my channel as well. If you scroll through here, what do we got here? There's a scope. There you go. There's the diagram we're looking for. I'll put a link to this website in the description below the video on YouTube. Okay. So this is what you get. You get a start bit. You get your 8 data bits. Notice the least significant bit comes first. Most significant is last, followed by a parity bit, which I happen to know is odd parity. So if you take all the data bits and the parity bit into account, there should be an odd number of ones. Okay. And there's a stop bit down here. Now, the main reason we're here and I've showed you this before, but what we need to understand is the falling edge of this clock is where we need to be sampling. As drawn, I mean, this is a nice way. If the keyboard actually sends its data like this, it would be great. It wouldn't matter what edge I sample on if it's stable during both of these edges, okay? So the real question then ultimately becomes, which one do we want to use? And technically, you want to use the falling edge. What you do is every time there's a falling edge, you look to see what the data is. If it's low, it's a 0. If there's a falling edge and it's high, then you got a 1. Like the stop bit will always report as a 1 during this falling edge. Otherwise, you know there's been some weird noise on the line, or your logic is not in sync with the keyboard that sends us all the clocks and the data bits. So to that end, every time we get a new data bit, what we want to do is we're going to concatenate it with the existing data in the RX reg. We're going to put it into the most significant bit. Now, you get the least significant bit first. Why am I putting it in the most significant bit? Because what happens is every time we get a new bit, I put it in the most significant bit. I notice the 0 is not in over here, so then I take all the prior most significant bits from RX reg, and I throw away the least significant bit here. This is me shifting over RX reg. The 9 through 1 bits go in through 8 to 0 in this expression here, and the new number 9 bit is the one I just got. So the very first bit that comes along will go into the most significant bit, and then when the next bit comes in, the first one will get shifted over towards the least significant bit position, and after you get 10 total bits, the first data bit will have been shifted all the way down to the least significant bit position. The rest of the 7 data bits will be left in there where they belong, and the most significant bit, as I mentioned earlier, will have the stop bit in it in the RX reg register, okay? So that's what's going to happen over the course of time as we get negative edges on this clock. We also are going to count every time every time there's a negative edge, the count will equal its current value plus 1 modulo 11. So it'll go all the way up to 0 through, why do I say modulo 12? It'll go up from 0 through 10, which is 11 total values. Oop. I still mess up. 11 total values, and then it'll go back to 0 again. All right, so they'll go from 0 to 10 in decimal, or 0 to A in hex. Okay, and around and around and around. Okay, so this one down here, what does this say? If the current count value is 10, we know we've just completed the read of an entire scan code, a whole byte from the keyboard. So on the next clock tick that comes along, which would be the stop bit, I want to assert the ready signal to let the user of this module know that the data coming out of the RX reg is valid. Okay? And that's how it gets out here. We saw that earlier. And the ready reg gets propagated out of the ready port right there. Okay? So look closely at these numbers, right? I don't think I'm just sticking it into the register because this is shifting. This is a modulo 11 counter, which goes from 0 to 10. And when we're on number 10, we know that we've just seen the last one, and it's time to assert the ready signal, okay? So, all right, how do we make sure this thing works? Let's look at the test bench. Okay, so I'm going to simulate this stuff that comes from the interface, the reset signal. We get the data, the clock, and this is where the data will come back, including the parity bit, and the ready signal that comes back out of the PS2 interface right there, okay? The usual thing, we're going to create a dump file and dump everything out. We're going to start with reset not asserted. And the data on the clock, when the keyboard is idle, are both ones, they're high. So these are not asserted either. Then we're going to come in here. What are we going to do? We're going to wait a little while. We're going to assert reset, wait, and then deassert the reset. Then we're going to wait a while and make sure that resetting this thing works correctly, okay? And by that, I mean we need to make sure that the right value is in the counter and things like that, because when the first byte arrives from the keyboard, our clock has to be set to 0. And this is why, one of the reasons why this is a naive design. If you do not reset this, and or if for some reason, due to noise on the clock line or something like that, the RX reg is not set to 0 when the keyboard is idle, then it won't count the right number of bits before it asserts the ready signal down here, and it'll just not do the right thing. Okay, this is terrible design, because there's no way to get this thing resynchronized unless you manually reset it with that S1 button on my FPGA board. But for testing the electrical interface and sanity checking this thing, it's perfectly fine. Okay, but I'm just saying, be careful. So this gives us a chance to look at the waveform, make sure that when the reset is deasserted, that the count values and stuff are right before we start playing around, sending in start bits and playing around with the clock. Now, I'm going to set the start bit before I put a falling edge on the clock, because the falling edge on the clock, remember, is where we want to be sampling the data. I'm going to wait a little while, and then I can move it back high again. So what happens here? We talked about for loops a while ago. This actually kind of like generates source code, and this loop would be unrolled, right? And then if you wanted to synthesize this, that's what would happen. In a simulation, it'll actually execute the loop and go round, round, round. Where am I going with this? What I want to do is I want to do this 8 times, where starts from 0 and it goes up to 7. Every time through the loop, I'm going to add 1 to I. That's going to give me my counter. If I is less than 6, that means during 0 through 5, I want to send a 1. After that, I want to send a 0. And the idea here is I just want to send some 1s followed by some 0s in the data portion of the message, so I don't have to type so much. Because every time you update the data, you got to take the clock to 0, wait, and take the clock back to 1. Now, if you really want to, you can actually save some vertical space, and you can do this if you want. And this is very common. I don't even think you have to have the semicolons in here. That just simply says wait 1, then do the stuff on the right. Okay, if you want to do that, that's what that means. I tend to like to keep everything on its own so that the order is like in your face. All right, waste some vertical space, but I'll get over it. So what are we going to do after all the data bits are sent out? 0 through 7, that's a total of 8. We're going to send out the parity bit. And if you count the number of bits in here, we need 1 more on in order for the parity to be odd. But this circuit doesn't even check the parity or even care. It blindly throws it away. So it doesn't matter whether you even put the right value in here or not for this particular test bench with this circuit. You then have to clock the clock line in order to move that state machine forward to take the parity. Then we got to send a stop bit, which is always a 1, and clock that. And then I wait a little while. And then I send a start bit, and I send a whole nother data byte. And as you can see here, I just say I and 1. And what this is going to do is it's going to set every other OTH. There we go. Every other bit, right? So the first time through the loop, I is 0, so this will be a 0. Second time through the loop, I is 1, and it'll be a 1, and then it'll be 0, and I is 2, and so on, because this is asking is the least significant bit in the binary representation of I is 1 or not, and that's what it's going to do. So it'll be what is that going to go? It'll be an AA, I guess. And then I'll have an even number of bits in it, so that should have an odd parity if we do this right. And then we can clock the parity bit out, and then the stop bit out. We wait a little while, and we stop, okay? Get rid of some of this vertical white space. Alrighty, and as is the case, I have a make plot in my make file that should just do this. My Pi exports to my desktop through X with a remote display. I can't wait to upgrade to Wayland and see how well that works someday. That's a whole nother story. All right, so what I did is I just said take every signal from the unit under test, throw it on here, and I click this little dingus right there, which means scale it to fit on the screen. Thank you very much. So what do we got here? We got a lot of junk we don't really need to be looking at that's cluttering the thing up. All these nexts can probably go away. I talked about, these Moore style state machines and how the combo feedback circuit works and all that. And that's what's stored in these next variables, right? I'm going to go ahead and just delete them to get them off the screen. I'll leave it as a task to the viewer to go through and make sure this makes sense if you want. So we got the clock and the data. We got a reset line. We got a count register. That's going to count up to A and then back to 0. You see it happening while this first byte arrives. Then we've got what? The RX data register that fills up 1 bit at a time with the serial data here that's picked off on the falling edges of the clock. We have a ready signal that's just assigned a ready reg. So we don't really need to see this either. Let's get that out of the way. And then we have the RX reg, which is just assigned to data. I'm going to put this down here and then underneath there as well. And the reason I do this is because the reg and the data have a relationship where, notice this is 9 to 0 and that's 8 to 0. So the data, remember, is the low order 9 bits of this reg. That's why when all these bits are high in the most significant part of the value of RX reg, let's go ahead and turn on the wave highlight. I like to do that. Keep so that I don't start pointing at the wrong row over here. RX reg, you can see the most significant 2 bits are on. Remember, this has got 10 bits, so 8 of them are in these 2 hex digits there. And bits number, 8 and 9, if bit 0 is over here, at least a bit. Bits 8 and 9 are both high right here. And you'll notice that this one doesn't have a bit number 9, which would otherwise be 0 because obviously we don't have that many bits. All right, so that's why these two have the same value, but this one here is the value that has the most significant bit truncated away because it will always be set high anyway because it has the stop bit in it, okay? So let's look and see what's going on here. During reset, we zero out RX count and we zero out RX reg. And that's what's happening when this goes high. Before that, it's unknown. RX data is given from reg. It's just assigned to that, so that's why that goes there. And RX ready, it comes from the RX ready reg bit that I pruned off the screen already, and that's also set to 0 during reset as well. So that all makes sense there. So reset goes high, comes back down. Okay. When the clock and data are idle, they're high. I said that before. Data is going to go low here before the clock falls to make sure that we recognize the start bit on the falling edge of the clock. Let me zoom in a little bit on that over here. There we go. So the data is going to be here, and every falling edge, the data will be stable. There'll be a setup period here and a hold that comes after that. So generally the keyboard would try to change its value on the rising edges or somewhere in here, like you saw the diagram from that university image I showed you earlier, so that you have a clean setup and hold time when you sample it into your circuit, which is why I didn't bother to put a synchronizer on here, because these signals are already synchronized to themselves, and that's all I'm using in this design. So it's perfectly fine. Okay, so when this falls down, the count advances to its next value, because that's what it does, right? Until it gets up to 11, at which point it's modulo 11 rather, until it gets up to A, which is 0 through 10, its 11th value. It wraps back to 0 over here on the next active edge, falling edge of the clock. And it does that when it clocks in its stop bit right there, okay? Alrighty. So the counter looks good, provided that we have the right number of bits up here, right? So let's go ahead and look at this here, right? If I highlight that row and I hit the right arrow, it'll stop on each one of these edges. So there's the first falling edge, there's the start bit. That's bit number 0, 1, 2, 3, 4, 5, 6 is low, 7 is low, and then you got a parity bit and a stop bit, okay? And then we are idle until the next message arrives. So far, so good. The counter's counting the RX reg, which clocks in the values of the bits as they arrive. Now, when that first edge comes along, what we're doing is we're clocking in the start bit. And because I don't even save it, ultimately, this bit is 0, so that's why the value doesn't change. You don't see anything changing here. It's still 0, but it's going to shift that 0 in all the way through and throw it away from the bottom by the time we get over here, okay? So it does put this into the register due to the simplicity of the circuit, but it ultimately gets thrown away. So this is the first bit that we care about. It just so happens to be a 1. It goes in the most significant position, and because we have 10 bits in there, the most significant bit is 1, and we end up with a 200. That makes perfect sense. When the next bit arrives, which is right here, we see with 300, because remember, a 3 is a 1, 1, and those are the 2 1 bits we've gotten so far. Then we get another bit that's a 1, and that means the 3 stays a 3, and the least significant bit of the 3 here shifts over to the right. That's why you got an 8. You shift in another 1. You end up, you still got a 3, and the 8 becomes a C, because a C is a 1100, and you shift in another 1 bit. You got an E0, because an E is 3 1s followed by a 0. We shift in another 1, and now we got a 3F, right? Because you got 2 1s, and then 4 1s, and 4 0s. The next falling edge is a 0, so the 3 becomes a 1, because the 3 is a 1, 1, becomes a 0, 1. The F is still safe, because the least significant bit of 3 moves into there. The least significant of the F there moves down to the 8 here, and we now have an FC, because that's what happens when you move it right and you bring in another 0. That 1 moved into the F, the F moves into the 8, the 8 moves down to the C, and so on. We're down here to 27E now, and that's because we clock in another 1, and now we clock in the last bit, which is a stop bit, which is always a 1, and that means the 2 becomes a 3, but we get a 3F now in the data field. We throw away the most significant bit, which is the stop bit, and we send it back to the user through this port here, in the form of a 1 for the parity bit and 3F for the value. And that's exactly what we had hoped to get, because 3F, F is 4 1 bits in a row. The 3 is 00 11, so that's a total of 6 bits in the least significant position, followed by 2 bits in the most significant position of this byte with an odd parity bit. So there's your 6 bits of 1s, and your most significant 2 bits of 0s were clocked in right there. So this works perfectly, and when the very last bit is clocked in on the falling edge of the stop bit, you'll notice that RX ready goes active right here. Stays active until the next byte arrives that it's going to get. And now this one, as you recall from the test case, we got a start bit followed by a 1, 01, 01, 01 as the thing runs, and a 1 parity and a 1 stop. And that looks right here. And when we're done, same thing, shifted all the way through. And you can see that we got a 3AA, which is really a 1 for the parity, followed by AA for the data, because an A is a 1010. And a 1010 for the other A. And that works perfectly as well. We can also see that RX ready goes high and stays high on the last bit, which is, of course, the stop bit. And that's because that's what the circuit does. There's no other clock that runs. It doesn't have an oscillator that free runs, at least in the PS2 interface module, so it doesn't have the notion of giving you a single tick with a single pulse to let you know here it is and then it shut it back off. This is completely driven by this clock right here, and the finite state machine cannot proceed unless there's a clock from the PS2 interface. So that's why it acts the way that it does, and it's one of the reasons it's so simple and doesn't need synchronizers and all that other fun stuff. So let's go ahead and program this thing up and see if it works. All right, so here's the rig. If I darken this a little bit down here, right, now I'm going to go ahead and hit reset. I'm going to hit the space key. You should see on the LEDs, there we go. There's your 29. If I hit my enter key, what do we got on that one? It looks like a 5A, which I think is the right thing, right? Spacebar 29, enter key 5A. Now you can't really see, maybe you can see a little bit of flicker. If I hold the key down, it doesn't want to flicker, but what happens is if I press the key, we see this. If I release it, you can see a little flicker in the upper left corner. Sometimes, like there it is, you can sort of see it happening on this LED up here on the upper left. What that's doing is that's the release code that comes before the following 2.9. So it doesn't happen until you release the key right there, okay? So, I mean, this is not going so fast that you can't actually see that, is my point. Now, if we play around with the oscilloscope, we can look more closely and see what's really happening over the course of time. So here's me hitting the space key. This is the key down code for the space, right? So if we start, this is, yesterday, and over here is tomorrow in terms of time, right? So basically the start bit is here, and the least significant bits to the most significant are in this order. So let's read it from the end back to the beginning, because I always think of it in that terms. Anyway, most significant first, when you're, decoding binary in your head. This downward falling edge is clearly the stop bit, which is always high. This falling edge is the parity bit, which is a 0, okay? So the most significant bit that we should get when we're hitting the space key is a 0. We got a 0 and a 1, 0. That's a 2 in hex. Then we got a 1, 0, 0, 1. That's a 9. So there's your 2, 9 for the space key. This bit over there is your start bit. Now here's me hitting the enter key. Here's your stop bit, 1, your parity is 1. So we got a 0, 1, 0, 1. That's 5 in hex. Then we got a 1, 0, 1, 0. That's an A. So there's your 5A for the key press code from the keyboard. Now if I press and release the enter key really fast, okay, so I can actually catch on a single, scan, a single capture on my scope, the key down and the release all in one screen like this. I can then see what's going on. So this should be the 5A, that should be the release code, followed by another 5A, and even zoomed way out at this, you can actually sort of see that this one looks a lot like that one, and this is all ones followed by all zeros, and the break, the key release prefix is an F0, so it should look like that. If we zoom in on the left side, there's the key down 5A code there. And if we zoom in on the two keys on the right side, there's the release code, which we got stop bit, parity bit, then we got clearly a 1, 1, 1, 1. Let's zoom in a little bit more on this. We can see a little bit, all right? So we got a 1, 1. As a stop bit, parity bit, 1, 1, 1, 1, which is right there. This is clearly a 0, okay? 0, 0, 0, which is your F0, which is the key release, and this is your start bit here. And then you've got the 5A over here for the key code that has been released over here. Now, if all we ever wanted to do was read from a keyboard, and we would add a little bit of, maybe we'll put some error detection and some error recovery and stuff like that for synchronization timeouts and so on in the code. But for the most part, we've got an electrical interface. We can recognize what's going on. It makes sense. It matches our understanding of the dock. Not bad. Next time we'll look at how we can keep track of what's really going on, improve our state machine. Maybe we'll synchronize it to a free-running clock so that we can put some timeouts and error recovery and stuff like that in here, which will make it far more robust and truly useful if we want to use this in a real device. Once we've got that done, we can send codes out to the keyboard to reset it, or even control a mouse to initialize it and stuff like that. We got all kinds of neat stuff coming down the road. Like and subscribe so you don't miss it when it comes. Thanks for watching. I'll see you next time.